So good afternoon, everyone. I'm very happy to be here again. Let us get on with the task. Looks like, yes. So I've structured the talk in the following way. There'll be a bit of introductory blah blah regarding the science interest of searching for life on Mars. We'll talk a bit about habitability based on what we have learned from mission results. And then we'll dive onto what has been done in terms of searching for life on Mars. In particular, we'll talk about the Viking missions, and then recent results from Mars Express, Phoenix, and MSL. Once we have understood where we come from, what has been discovered recently, then we'll talk about what is being planned for the future, and in particular I spend a few minutes on the ExoMars missions that we are preparing in Europe and Russia. Then we look at the international scene for missions to Mars and say a few concluding words. So the interest of life on Mars has basically two main themes. The first one is that we know that early in the history of Mars, liquid water was present on its surface, and that some of the processes that were important for the origin of life on Earth may have been active also on early Mars. The other thing that is very, very important is that on Earth, when we try to glimpse what may have been the origin of life on our planet, we find ourselves with a big problem, and that is that we don't have access to well-preserved rocks from the time when life arose on Earth. You have heard from Francis that she's looking at studies of rocks of roughly 3.5 billion years of age. Now, we think that life started on our planet earlier than that, and the interesting thing is that on Mars we do have access to very ancient rocks. On Earth we have plate tectonics, which results in the subsidence of sooner or later of most parts of the Earth crust, and the reforming of the rocks. Basically, they get cooked at high pressures and temperatures, and they get degraded, and then we don't have access to well-preserved rocks. Mars, instead, is a much smaller planet. It may have had plate tectonics very early on, but certainly for the last few billion years, its crust has behaved as one unit. And from orbiting missions, by counting craters, we can identify regions on Mars that are very, very old, in the order of 4 billion years of age and more. So, conceivably, were we to find traces of life on Mars in very ancient rocks, we may be able, by extrapolation, to learn something about what conditions may have been like on Earth. So, first, interest on Mars as a possible, let's say, abode for life very early on, and secondly, a window to very old rocks that we no longer have for analysis on our planet. The final point of this slide about future human missions, it's, if you want, sort of a second priority at this point, because we are probably so far away from human missions to Mars. But it is true that before sending astronauts there, we should have a much better understanding of whether life arose on Mars, and indeed whether there may be life there active today. We should be very, very careful not to contaminate or indeed destroy possible life that may still be active on Mars. Now, space missions are the art of the possible, or a very complicated exercise on compromise. And you have seen in Francis' presentation all the wonderful techniques that she can bring to bear to analyze the rocks and the samples she's working on. Now, we cannot do anything even remotely comparable to that on a space mission. She already alluded to the fact that we are very limited in terms of mass, power, data return, and so we need to be practical. So when we try to prepare a mission to go search for signs of life, the first obvious question is to ask yourself, what is life and where are you going to go after? So the definition that you see here is one that has been going around for quite a number of years, and it's a pretty reasonable one. But as you see, it is very, very difficult to try to prove that something is a self-sustained chemical system that can undergo Darwinian evolution. It's very hard to measure or check evolution, and therefore you have to go for something that is less complicated. And we need a definition that is useful for a space mission. And what we can say is that as long as we stick to the things that we know, and here we're talking about, of course, basically carbon-based chemistry, I think we are on safe ground if we say that life is cells. And if we can detect things that are associated with cellular metabolism, then we can have a certain degree of confidence that we are talking about something that was alive. Now, in terms of elements of cells, here I've grouped a few things that you could consider common for cellular life. The need of liquid water, proteins and nucleobases, sugars, and the elements of membranes. Another important property of life on Earth is that of homochirality, which concerns a property of some important biomolecules that can exist in theory in two mirror forms. So if you produce them in the lab, you get equal amounts of the left and right enantiomers, whereas life specializes. And for example, on Earth, life is based on left-handed amino acids and right-handed sugars. So were we to detect an important, let's say, enantiomeric excess of, for example, in amino acids, either left or right, that would be a very strong biomarker. So in terms of what we can expect to search for with a mission on Mars, we can make a distinction in terms of present life, that is, life that is active today, cells that are metabolizing, and in such case, were you to scoop a certain amount of material and analyze it, you could probably expect to, if you're lucky, to find some of the key constituents of cellular life. Amino acids, nucleobases, sugars, phospholipids, which are the elements that membranes are made of, pigments like carotenoids, for example, that mediate important processes in cellular life. In the case of past life, if we're talking about something that was alive 4 or 3.5 billion years ago, that has stayed in the geologic record for all that time. And basically, if we're looking at organic molecules, we will not have access to the pristine molecules as in the case above. We will be dealing with organic residues of possible biological origin. And Francis alluded or talked a bit before about what types of compounds you might be able to find. We also may be lucky and be able to image and study textural evidence on rocks, biolaminations, and the types of structural evidence that may be left behind in microbial mounds, for example. And finally, there's one other interesting source of organic molecules that has nothing to do with life, which are the molecules delivered by meteoritic and cometary inflow. Now, both the Earth and Mars receive in the order of roughly 300 tons of organic material per year in the form of very minute micrometeoroid powder, if you want, that reaches the upper atmosphere. So when the Viking missions landed in 1977 on Mars, they were expecting to find the surface of Mars, I won't say coated, but they expected to find several centimeters of this material, organic material, on the surface of Mars, and that was not the case. So we know it arrived on Mars. It should be somewhere, and it would be interesting to find out where. So I'll move a little bit now to habitability, so the potential for a planet to host life. And I won't talk about in the same way that Francis did. It's a bit more an introduction to some of the key processes that we think are important to sustain life hospitable conditions. So we are talking about the fourth rock from the Sun. The Sun is a G-type star, and the habitable region around the Sun encompasses the Earth orbit. Venus is probably too close to it for its own good, although conditions may have been different very early in the history of the planet, when the Sun was much less bright, and when conditions on Venus and Mars and the Earth were more similar. So we're talking about the first 500 million years or so. Mars is in an interesting position because it is very cold today, and but as we will see later, things were not always this way. So if we look at Earth and Mars, and this is sort of the ID for both planets, you see that there are a number of things that are similar. For example, one interesting one is that both planets have seasons. That's the inclination of their orbital axis is more or less the same at the moment. Both planets have days with more or less a similar length. Mars is a lot smaller. It has a gravity that is basically 40% that of Earth. Although this is probably not very important in terms of search for life or origin of life things. One thing that is very, very interesting is that the atmospheric composition of Mars, with 95% CO2, is more than one that you would associate with sort of a dead planet, or for sure not a planet that has a very active biosphere. In terms of Earth and Mars comparison, interestingly enough, Mars used to have a magnetic field and may have had a magnetosphere very, very early on, We know this from the Mars Global Surveyor mission, which during its aerobraking phase flew very, very close to the Martian surface and detected the remnant magnetization of the crust. So Mars did have a magnetic field at some point. The magnetosphere is important because it has a certain protective effect on the upper, particularly the light constituents of planetary atmospheres, though we have to remember that Venus doesn't have a magnetic field or a magnetosphere and still has a very, very dense atmosphere. Plate tectonics and volcanism, very, very important. In the case of Earth, it's the way we have for closing the carbon cycle, from being able to sequester the initial very, very dense CO2 atmosphere that Earth and the other terrestrial planets had. We had plate tectonics as a means of getting that CO2 out of the atmosphere and into rocks. The Earth has a moon. The moon is very important. A large moon helps to stabilize the wobbling of the planetary axis. Poor Mars has these two very small potatoes for moons, and they don't do much for it. So it's, as you see on the lower right corner, the obliquity of the rotational axis of Mars goes through roughly a 50 to 100,000 year cycle and can oscillate quite a bit. So that parts of Mars that, for example, the poles are a certain under higher obliquity conditions would turn into more temperate areas. And this results in a massive, let's say, removal of water from certain areas and deposition on others. And finally, of course, Earth has liquid water available today. It's not the case with Mars, but conditions on Mars may have been different in the past. So roughly, today Mars is a frigid desert, very, very cold, with roughly 100 degrees difference between the day temperature and the night temperature, a very tenuous atmosphere, roughly 6 millibars, and as a consequence of that, very high doses of UV radiation and comparatively high doses of ionizing radiation as well. There's dust everywhere. The dust is the consequence of, let's say, the pelting the planet suffered during a meteoritic bombardment and the subsequent action of the wind. And this dust is not interesting at all for us in terms of finding life on Mars, because it's basically moved around by the wind and sterilized by UV. So, Mars was different in its very early history, probably the first roughly 500 million years. So let's move a bit now into the search for life. And if we talk about search for life, we have to start with the Viking missions. Two missions that were launched in 1976. Each had a lander and an orbiter. And these have to be the Rolls-Royce of missions to Mars. If you were to convert their cost to today's euros, we will be talking about something in excess of 10 billion euros. They were mammoth undertakings for the time. More so if you think that the missions were put together in the early 1970s, when there were no computers available. The most exotic piece of electronics that you could have at the time was a discrete transistor. And nevertheless, these missions did a lot, and very, very well. In terms of, I think I jumped over a slide. In terms of orbiter images, the first detailed photographs of the surface of Mars suggesting the past action of water came from Viking. Here you see these, on the left you see these dendritic formations that on Earth you associate normally with rain and the runoff of rain on surfaces. And on the right you see these sort of elongated islands that clearly point to the flux or the circulation of some sort of liquid. Also, another interesting thing that Viking found was that some large craters on Mars did not look at all like the craters on the Moon. On the left you see that beyond the rim you see this sort of splatter, as if something had been thrown that was wet. And this suggested at the time that there might have been subsurface ice that resulted in some sort of slurry that was ejected out during the impact. So this got people interested, not only in terms of past action of liquid water on the planet, but also in the possibility that that water, or part of that water, might be still available in the subsurface. In terms of results from the lander, well, this was the first time when we were able to get images from the surface, and they were really spectacular. And among other things, it was observed that many nights during the year there would be frost, so water ice that would be deposited from the atmosphere on the surface of Mars. And this is our further search for life beyond Earth, which are the trenches excavated with a robotic arm by the Viking landers. Now, we could have a whole lecture just devoted to the Viking experiments. They were really, really well put together. And the fact that in the end the results were deemed not to be conclusive in terms of the presence of life on Mars has a lot to do with the way the questions were put together. So the Viking landers included 3 biological experiments designed to detect the metabolic products of active cells, plus a GCMS, a gas chromatograph mass spectrometer. We will be talking quite a bit about GCMS. I'm not sure whether this has been covered in one of the other lectures, so I will spend 30 seconds explaining what it is. Basically, a GCMS consists of 3 parts. The first part is the extraction of the organic molecules that you want to analyze. So in the cases of, let's say, the usual missions, the way we use to extract molecules from, let's say, a spoonful of dirt is you heat up the sample, and sometimes that is called thermal volatilization or pyrolysis. You can do that stepwise, so you proceed from low temperatures in steps. Sometimes that is called calorimetry separation, and basically you cover a range up to, let's say, several hundred degrees, even 1,000 degrees, and as the gases become volatile, you get sort of a gas soup, so a mixture of gases. So the next thing you want to do, so step 2, is you want to separate the various species. And for this, you can use a gas chromatography column. This is a very long column that has, let's say, a particular packing material inside that separates the species or the gas constituents or molecules you had in your soup. the first step, you render them volatile, and everything is mixed. It goes into the column, and then they come out marching like soldiers, let's say, ordered from short to tall. So it could be, for example, from low molecular weight to high molecular weight. And after, you have the mass spectrometer, the third step, for being able to identify the soldiers that come out from the column. So one is Joe, one is Sam. So you use the mass spectrometer to ionize the molecules, you break them in pieces, you analyze the pieces, and you can say, this is this molecule or that molecule. So Viking had 3 biological experiments and a GCMS. The first experiment tried to see if there was something alive in the soil. And the way they did this is they put a fraction of a spoonful of Mars soil in a container. They removed all the atmosphere and instead used an artificial atmosphere that the mission created, which instead of using CO2 made with the normal carbon-12 isotope, used the radioactive carbon-14. And they incubated this bit of soil with a UV lamp in the presence of this atmosphere. Now the idea was, if there are active microbes, they will start doing something with this funny atmosphere that we put there for them. So we let them work for a few days, and afterwards what we're going to do is we're going to pyrolyze or heat the soil, see what organics come out. If the soil, if the microbes there did something with the atmosphere, we're going to see something in the radioactive detector. So we should see carbon-14. Very clever, very simple. The second instrument or experiment called labeled release wanted to see if there were any microbes that would eat. So they prepared some interesting snack for these microbes, and what they did was, again, they collected a bit of soil, they put it in an incubator, and they added a bit of this nutrient. And then they monitored what came out in terms of respiratory or gaseous byproducts. And they did this over several days, weeks actually, and there were more than one of these injections of nutrient. And the goal there was, again, that because they had used, for example, for the sugars, they were not made with normal carbon, they were made with, again, with radioactive carbon. They thought, well, we monitor the respiratory products. If we start seeing carbon-14, we know that something took place. The final experiment was a bit complicated, but basically they put, again, soil. They removed all the Martian gases by flushing with helium. Then they incubated the sample in the presence of water, nutrient, and CO2, and then watched for several months and with a GCMS to see what sort of stuff would be coming out. They monitor for CO2, oxygen, methane, hydrogen, nitrogen. So let us look at the results. I forgot to say one thing. These guys were really, really smart. And in order to try to avoid false positives, they heat sterilized to 600 degrees, a control sample. So not only did they have to be able to see signs of life in the responses to the sample they were looking at, they also had to see no life in the heat sterilized sample. So on the top row, in the center rectangle, you see what the response should have been had there been life. Below you see what the response would have been if there was no life. And finally you see what Viking detected. Now it's interesting that all three experiments observed chemical changes which, had they not had the control sample, would have led them to conclude that there was life on Mars. Because they had the control sample, the heat sterilized sample, they were able to see that some of the emissions happened also with the heat sterilized control. And this led some of them to think, well, maybe here we have something that is more inorganic in terms of chemical reaction. And one of the things that they were really concerned about was that the GCMS failed to detect directly organic compounds. So the results of the Viking mission, after quite a bit of discussion, were that the observations were probably more in line with the existence of some powerful oxidants, probably the result of UV photochemistry acting on the top Martian soil. Now, this does not necessarily rule out the possibility of life on Mars, past or present, but it definitely, let's say, increase the height of the bar in terms of what subsequent missions would have to do if they would like to search for life on Mars. I'm trying to get the slides to move on. Okay. Before I talk about Mars Express, I should say that after the results of Viking, let's say 1977, there was quite a bit of discussion, probably until the early 1980s, about what the results meant. There were some people, there still are some people that think that Viking actually did detect something related to life. So there was a group of scientists in Europe that were tasked with reformulating or thinking of what would the next step have to be to try to look for signs of life on Mars. And we're going to see that that gave rise to what is today the ExoMars program. But I think it's important that you understand that this thinking was done in around 1994, 1995, in the time between, let's say, Viking and the MER missions. So, one of the things that a lot of people were puzzled about was, okay, so Viking saw plenty of surface signatures for the past presence of water. And on Earth, it's interesting that a large part of the organic matter concentration is correlated with the availability of increasing mineral surface area. So typically, small clay particles are very good at sequestering organic matter. So as a degradation product or as a degradation process of rocks proceeds, you have an increasingly large fraction of the remaining organic matter that is protected because it's associated with certain mineral surfaces. So clays are a good place to look, and there are also other types of minerals that are also good at protecting biosignatures. But in particular, clays were, let's say, a tricky point. So between Viking and Mars Express, there have been other orbiters going to Mars, and they had not been able to spot clay. So it was a wonderful result of our ESA Mars Express mission when in 2005 the infrared mapping spectrometer, Omega, detected many instances of phyllosilicate clay sheets. So finally, we had, let's say, not only the clay detection, but also the interesting fact that these clays or these phyllosilicates were observed in ancient terrains, suggesting again that the young Mars was a planet that had been shaped by liquid water. Now the bottom right shows a recent paper from Bethany Ellman. There's quite a bit of interesting debate as to what extent these clays may have formed through subsurface water processes or surface processes. But the important thing is that they were there and that they point to aqueous water environments. More recently, we have the Phoenix lander launched in 2007. Now, Phoenix landed in the subpolar regions of Mars in the northern hemisphere in May 2008 and operated for 150 sols. Like Viking, it used a robotic arm to collect samples of soil and then deliver these icy soil samples for analysis. And a very interesting result of Phoenix was it had a wet chemistry laboratory. For the first time, wet chemistry analysis was performed on Mars, and the wet chemistry lab detected 0.5 by weight % of perchlorates in the soil, and this was a big surprise. Perchlorates are pretty exotic molecules. On Earth you find them in very high dry deserts, and they're the result of UV photochemistry acting on let's say chlorinated compounds, atmospheric compounds like HCl. But it's a very interesting molecule because we use it as a fuel oxidizer for rocket engines. So perchlorate is a pretty neutral anion. It doesn't do much unless you heat it up. When you heat it up, it really goes berserk. It releases all those oxygens, and there's so many of them, and they're so aggressive and reactive that you get really, really fast, dramatic oxidation processes. Now, it's interesting also that the TIGA, which is an evolved gas analyzer, so it basically heated up the samples and analyzed the results with the mass spectrometer. So it didn't have a gas chromatography column to make the separation. It just analyzed the whole soup coming up and did not detect any organic gases through this calorimetric step heating up of the soil samples. Now, a lot of people started thinking about this, and some people suggested that maybe the way we had been looking at for organics on Mars by heating up soil samples was or could be part of the problem, because if you had very aggressive oxidants like perchlorates, which become active when you heat up the sample, maybe it was this oxidation process that was degrading the organics. And some people went and looked at the results of Viking and discovered or remembered or rediscovered that Viking had indeed detected organic molecules. He had detected chloromethane and dichloromethane, which at the time were thought to be, how should I say this, residues of some of the agents that have been used to clean the instruments. Okay, so some people say, wait a second, if you see chloromethane, maybe what you're looking at is maybe there are perchlorates in the soil. When you heat, you oxidize the organics, and this poor chlorine atom that is going around, what should he do? So he chlorinates something. So maybe this chloromethane is the chlorination of part of a possible organic molecule that may have been part of the soil. And the lab results that have been carried since confirm that if you put organics in the presence of perchlorates and heat them up and try to analyze them with GCMS, you get, let's say, how should I put it, a complication of the results. So you get at least a partial or a total oxidation depending on the molecules of the organics you're trying to analyze. And recently, by the way, with the first analysis from MSL of the Martian soils, they also detected chloromethane and dichloromethane. So this is an interesting new result, and it's something that the community looking for organic molecules on Mars is taking very, very seriously. I'll jump over this slide. It basically makes the point that, and this is an important result of the study I talked to you about in the early 1995, 94, that makes a case that if you want to look for signs of life, whether it's past or present, the subsurface is a place to look into. We'll come back again on this slide. There are a number of organic destructive agents that exist on Mars, and this is due to a very tenuous atmosphere. First of all, you have UV radiation, but this is light, so it doesn't penetrate much into the soil. The second thing is you have very aggressive oxidant species, the result of UV photochemistry. These perchlorates could be one, but hydrogen peroxide is another. And they will tend to diffuse into the soil depending on the porosity, on the water content, etc. Depending on whose model you believe, they could go down into the soil a few centimeters up to a meter. Finally, the third, ionizing radiation, it's a very slow process acting over hundreds of thousands of years that cleaves at the functional bonds of molecules, degrading them, and eventually rendering them undetectable by our instruments. So, one of the very important things that we want to do with the ExoMars mission is, and is a result of this study of 1995, is go and collect samples for analysis below this degradation horizon. So if you look at the image, you can see that there is a bit of outcrop sticking out. That is a bit of outcrop that we can look using remote analysis, for example, from an orbiter. So you would look for the right type of mineralogy, the one you think would be good at preserving biosignatures, carbonates if you can find them, or clays, or certain salts that you can associate with hydrothermal deposits, etc., etc. And once you land in a place where you have these interesting outcrops, you don't look and analyze the surface of the outcrop, but you try to go and collect the material from the subsurface, where it has been protected for hopefully very many millions of years from degradation. So I'll describe very fast now the ExoMars mission, which is what we're working on now. It has an orbital component. The orbiter will go in 2016, and it will concentrate on the analysis of trace gas elements in the atmosphere, of which particular interest is methane, which was first detected by Mars Express, because it could be associated either with some geological activity on Mars, for example, serpentinization of rocks in the subsurface, producing hydrogen, which then combining with CO2 would lead to methane, or indeed it could be associated with the presence of subsurface bacteria. Another element of this first mission is an entry, descent and landing demonstrator, which hopefully will teach us Europeans to land on Mars. And it will have a very small payload. Now we work over a few days to conduct some meteorology measurements. But here we have the composition of the payload. We have an interesting cocktail of infrared spectrometers in the NOMAD and the ACS instruments, a high-resolution stereo camera, which is CASIS, and a neutron spectrometer that will provide us maps of subsurface water and hydrated minerals with improved resolution. So another thing that we will be able to do with this mission is look at the ratio of deuterated water to water in the atmosphere, and that will give us an indication of the evolution of atmospheric water in terms of escape to space. A very interesting mission. The ADM, again, as I mentioned, roughly has a very small meteorology station. Its main goal is to land. And then we move on to the more interesting mission from the point of view of exobiology, which is the second mission going in 2018, whose objective is to search for signs of past and present life on Mars, which is the ExoMars rover. It will land using a Russian lander. I should say that ExoMars is a cooperation program between ESA and Roscosmos. So Roscosmos is providing the launcher for the first mission in 2016, and the launcher and the lander for the second mission in 2018. And this mission will put the rover on the surface, and will also have a few instruments in the platform. So after the rover leaves, the platform will also conduct some sort of science mission. We don't know yet because we haven't selected the instrument. But let's talk a bit about the rover. These are the latitude bands where the rover can land between -5 and +25. And the areas we're interested in are the very old areas where we think we might have a chance to find ancient signs of life. But we have to land at low altitude. So here you see in green are altitudes where we have sufficient atmosphere in order to use the parachutes. It would be nice to be able to land in the red or the orange areas, but they are simply too high. The rover is the main thing you notice about the rover is that it has this big box in the front. That's the drill. The drill can access the subsurface down to a depth of 2 meters, and it's like a mini oil platform. It assembles 4 rods in order to reach its full extension. And in the lower right corner you see this white rectangle where it is shown how the drill collects a little sample, and then that sample is brought up to the rover and analyzed. But in order to carry out its mission, the rover has to cover a number of different scales. So it has to be able to observe things from meter scales all the way down to molecular scale. And this you have to do by nesting the various observations in terms of scale that you carry out. And we also learn by subsequently performing these analyses. So we characterize the surface geology, we look for structural biosignatures on outcrops, we explore the shallow subsurface stratigraphy, identify candidate sites for drilling, we drill, we search for biomarkers, we see how things change with depth, and we get better at predicting what we're going to find the next time we try to drill. And hopefully, by repeating this cycle a few times, we will get more efficient. The instruments that we have are a panoramic camera system. This is stereo cameras, roughly 50 millimeters equivalent in terms of photography objectives, with a high-resolution camera in the center, which is the equivalent of a 300 millimeter objective. There is also an infrared spectrometer on the mast that points where the high-resolution camera points, and that tells you a bit of information about the bulk mineralogy of rocks. And this is used by the rover to decide where to point for high-resolution images, so that when we get the results on the ground, you get a nice panorama, and then embedded in that panorama there are a few areas where you get high-resolution imaging and some mineralogy information. Then we also have two instruments that will help us to understand where to drill. A ground-penetrating radar provides a stratigraphy under the rover, so we know how far away from the surface are the layers we want to access. And a neutron spectrometer tells us about the water content of rocks or the level of hydration. For example, if we're looking for clays, it's interesting to know how hydrated they are. This gives you another view of how the high-resolution camera images are embedded in the wide-angle camera images. Another important thing is, once you find something you think is interesting, for example an outcrop, here you just see a rock, but hopefully it will be an outcrop, you get close to it, and then you want to analyze the structure, understand more about the microstructure and the deposition environment that gave rise to that outcrop. And for that we have both a high-resolution camera and, crucially, a close-up imager that will allow us to study things on micron scale. And then you have to decide if you're going to collect a sample. You collect a sample either from the outcrop or from the subsurface. The sample is collected with a drill. The drill has a miniaturized infrared spectrometer that looks through a sapphire window on the side as we drill, and provides a bit of in situ mineralogy information. The sample is brought to the surface, is imaged again with a close-up imager and the high-resolution camera, and there is like a little hand that comes out. The sample is deposited in there, and then it goes into the laboratory. The laboratory is a very complicated piece of equipment, and this is what happens inside. The sample is crushed, is first analyzed with an imaging infrared spectrometer, is visible and infrared. So it's like collects an image, but instead of this usual red, green, and blue image, here you have 500 different colors in infrared bands, spanning from 0.9 to 3.5 microns. So we will be able to cover clays, salts, crucially carbonates, and because it's an imaging spectrometer, it can tell you, by looking at the bands, it can tell you the pixels in let's say, in sample space, where you have clays or where you have this or that type of salt. So then we can use that information to move the sample under the instruments like the Raman spectrometer and the laser desorption mass spectrometer, which are point and shoot. If you didn't have this information, you would be shooting blindly. But if we can use micro-omega to tell us where the sweet bits in the sample are, then we can fire our laser with more confidence that we're going to find something interesting. And if we find something interesting in terms of organics, then we can engage the second part, which is the part of MoMA that has consumables. We will have 35 little ovens, but each one of those ovens we can use only one time. So we use first the laser desorption mass spectrometer, which we can use infinite times to find where the interesting stuff is, and then if we find something interesting, we can use the other part of MoMA. I'm getting to the end. If you look at cosmic distribution of organics, you find that there are a lot of organics in space. And usually we're talking about small molecules with let's say, a few carbons in the chain. And the bigger the molecules, in terms of carbon atoms, the fewer or the more sparse they are. Now, life, on the other hand, tends to specialize and therefore uses a few molecules in certain families of molecules. And so, in the case of life, we would expect to see this more fingerprint type of distribution of organics. However, we cannot be sure whether it will be, so the main organics detection instrument we have in ExoMars, MoMA, is a broad organics detection apparatus, which will give us a good chance to find organic molecules. So this is the summary composition of the payload and the countries that are involved, and I think it's better you see this from the presentation once you have it in your hands. Getting to the end, there is something called the reference surface mission, which is sort of scenario that we put together to see what sort of interesting science we could do with the rover. Only 2 points I want to make with this slide. One is that one of the first things we have to do when we land on Mars is run a blank through the analysis, and hopefully the examination of that blank will tell us that there are no organics and that we are clean. This blank is the way we have to prove to the scientific community that we have not taken with us any organic molecules from Earth. So if we do this analysis and show that the results are no life and no organic molecules, at that point we get a clean bill of health to start the science of the mission. The other thing that is very important is that the quality of the results we're going to get with ExoMars will depend 100% on where we land. We have to land on the right place for the sort of mission we want to do. I mentioned already that we cannot land in a place that is a dust bowl, because the dust will not contain any organics information. Will not have any textual information either. We have to go for places that have numerous instances of juicy outcrops with the right type of mineralogy that is good for the preservation of biosignatures. So, international. We are embedded in an international context. And you see, right now we have MSL on the surface of Mars. And at a certain point, we will want to bring samples back to study on Earth. And ExoMars fills a super important niche. And that is, for the first time, we will be able to access the third dimension on the planet, which is depth. If we're going to bring samples back to Earth, we need to know where to collect them from. And it could be, and a lot of people think that this may well be possibly the case, that the chances for the preservation of organics are much better in the subsurface, beyond a meter depth, than they are on the surface. So MSL will do great science on the surface of Mars, and hopefully will work for many, many years. But we think that also ExoMars, with its search at depth capability, will be very, very important on the way to defining a future international Mars sample return mission. So my final slide, I'm sorry if it has been a bit longer than expected, is that ExoMars is very, very interesting. The trace gas orbiter will make a first attempt at confirming the presence of methane on Mars, the interesting chemistry happens there, map methane on the surface of Mars, and understand its sources and sinks. And this is an important gas of potential astrobiological relevance. The rover we'll also conduct a super interesting exobiology mission complementing the results of MSL, going to a different place, and for the first time searching for organics and structural biomarkers, in particular for organics of past and present life at depth. And we'll also be able to tell us about how things change as we go down in the surface. I will conclude with this. There's a lot that I could tell you about the new technologies in the rover that are a step beyond what is moving on Mars today. But I think this is enough. I think Mars sample return is very important for the scientific community, and all of these missions are a little step in the right direction. Thank you very much.
Yes, thank you very much. It was a very, very fascinating lecture. Just a theoretical question. Might it be a possibility that around the pores on Mars, the structure of these geological structure might be different, and might it be that the radiation levels and the radiation creates a different pattern, a different structure. So might not it be an idea to search for life around the pores on Mars? It's just a theoretical question, so it might be bad in a lot of places.
Well, thank you for that. A lot of people actually advocate the polar areas or the subpolar areas as very interesting places to conduct exobiological missions. The truth is that if looking for life of Mars is complicated at lower latitudes, it becomes really, really difficult when you try to get close to the pole. You would need a nuclear-powered mission almost for sure, because something as short as Phoenix, which was solar-powered, in 100 and some sols, you cannot really conduct very complicated protocols like what we're aiming with ExoMars or indeed MSL.
Yeah.
So, yeah, interesting but complicated.
Need lots of power. Thank you very much.
Thank you. So I would like to thank Jorge very much for the very nice lecture. And I have a question which is actually always the same, because, okay, I understand that to detect life on Mars is difficult, but what about water? We know that on the moon there is water. One can say, well, the moon is near, but also on Enceladus we know that there is water. So what is the difficulty to find water on the surface of Mars?
Okay, thanks for that. Well, today water on the surface of Mars is possible only as ice. Liquid water is possible in the subsurface, but probably fairly deep, in the order of a kilometre or so. So it would be great to have found some sort of hydrothermal activity where we could sort of remotely detect a hotspot, because we know there is ice in the subsurface. At the poles you can see it on the surface, and in the subsurface, let's say down to 45 degrees, Odyssey with a neutron spectrometer has detected out ice within the top 1 meter. So I think there is a reasonable chance that you could land somewhere and drill not too deep and find ice. And liquid water is a more complicated story. A lot of people have been looking at the association of water with with salts, because the presence of salts in let's say brines or salty mixtures can have a depressed eutectic solidification point. So you could have let's say a liquid watery or solution at a lower temperature, but probably not so great for microbial life. So water uptake is more complicated. I don't know if I have answered your question. I think it's finding water, I think, is not so much of a problem, but finding liquid water is complicated.
Okay, thank you a lot. Yes, you answered my question, and I have a question by Adam Watsne, so I'm giving him the floor.
Thank you for lecture. And I have a bit of engineering question. That is, I saw on slides that you are going to land the rover on a platform, and the rover then will go from the platform by some slopes. And isn't this method a bit risky, because similar methods of one of the previous rovers had some problems? Isn't, for example, crane better?
Well, yes. I mean, there is the potential. There are a number of complications that could happen with landing and then having to deploy ramps to get the rover down. For example, you could land on a slope. You could land on top of a rock and have the platform inclined. When you deploy the ramp, or let's say one of the ramps can go on a rock, and then that ramp you cannot use. So yeah, there's a certain degree of risk. On the other hand, landing with a sky crane is not free of risk. In fact, a lot of people thought that the Americans were quite crazy to try something like that, and people thought there would be a high chance for it to go wrong. Now that it has worked, everybody thinks it's a great idea. But doing something like that is very complicated. The other thing is, you have to remember that certainly Europe hasn't landed successfully yet. Russia did a long time ago. Actually, they were the first ones to land successfully on Mars. But again, it was a totally different type of setup. So a lot of people think that this sort of landing approach is inherently less risky from the point of view of landing successfully, but is more risky from the point of view of putting the rover on the surface. So basically what it means is we will have to find a place that with few challenges in terms of egress. That is what we call the rover getting off the platform. It will be interesting and difficult, but stay tuned if you're interested, because probably before the end of 2013 we're going to release the first call for landing site proposals, where we will ask the international science community to propose locations for ExoMars to go to.
Okay. Thank you very much.
Thank you very much. And I think there are no more questions, so I would like to thank all the speakers of today, and to wish to everybody nice Christmas holidays and a Happy New Year. Bye. Thank you.
Thank you. Same to you.
Francis Westall, do you have any questions for Jorge?
Yes, I do. Can you hear me?
Yes,
you can.
Okay, great. That was a fantastic talk, Jorge. Thank you very much. I really, really enjoyed it. I've got a couple of things that I'd like to ask about the drill, because the main advantage of ExoMars over other missions is the fact that of depth penetration, and supposedly the ability to get below the superficial, oxidized and radiated surface. Now, I'm thinking in terms of normal sedimentation. In normal sedimentation, you get one layer upon another. So let's say you have a surface layer on Mars. It's exposed to oxidation, to radiation. Then it gets covered by another surface layer that's exposed to oxidation, radiation, and so on and so on. If you drill down 2 meters into that, you've still got material that's oxidized and has been exposed to radiation. Well, that's one comment. The other thing is that in your diagrams you show the drilling into an underground portion of the outcrop that we see at the surface. There are limitations as to the power of the drill, what the drill can actually drill into, because the drill can't drill into basalt, so I've been told. And, you know, the volcanic rocks are basically the rocks that we'll be encountering on Mars. Is there any way of improving the performances of the drill? Is there any way of... Actually, I don't know. I don't think there's any way from the surface of understanding whether the subsurface material is just surface. Well, understanding the oxidation state and radiation state of the subsurface material. Sorry, it's not a very clear question, but I'm worried about not being able to reach the objectives with the drill.
Okay, so I understood 2 different things. I mean, not 2 different things, 2 points. So I go through to the first, and that is, sure, you could have different layers being deposited at different times, and well, hopefully if we land in the right place, the sort of layers would have been deposited at a time when the atmosphere was much denser, and therefore no ionizing radiation and not UV photochemistry. That's sort of a wish. But even had they been exposed in a radiation-rich and let's say UV photochemistry / oxygen-rich environment, if there was life, and at the time the life was sort of relatively rich, obviously it was dealing with whatever conditions that were there at the moment. The process of radiation doesn't worry me too much, because that is a very slow process. The radiation dose is not that high. The problem is that it's there all the time. So the fact that the biomarkers or the putative cells, whether they were dead or alive, would have been exposed to radiation for, I don't know, even a few tens of thousands of years, because they hadn't been buried very deep, it probably wouldn't do too much. The oxidants, I don't know. So I think if the how should I put it, the entombment of the material was relatively rapid and led to reasonable preservation conditions, and then it was covered by other layers, that's not such a bad thing. Now, if you have 10 layers on top of the other, and they're all sedimentary, there's no way that we can get to the, let's say, the bottommost layer with a drill. I mean, we could, but then we would be drilling in one single place the entire mission. The progress of the drill is roughly 1 millimeter per minute through very loose soil, and about 1/10 of that through hard rock. So actually, you could say maybe up to 1 centimeter per minute if it is really, really loose. But the way we expect to use a drill is we really want to use the loose material, the regolith, as some sort of protective agent to get down to sedimentary material. And once we get to the sedimentary material, only penetrate a few centimeters to collect the sample. Okay, so that's point one for the scenario. Point two has to do with what sort of rocks we can deal with a drill. The drill has to do two things. It has to get you through the rock to where you want to go, and it has to do that in such a way that A, it doesn't get stuck, and B, it doesn't heat up your sample to the point where all your, let's say, biomarkers are going to be cooked. So, the normal recipe for not getting stuck with a drill, and believe me, we have tried with different drills and a number of campaigns, if you go fast, you get stuck. If you go slow, then you're okay. And the drill goes very slowly. Try this at home when you're drilling through a concrete wall, not through bricks, because through bricks is very easy. But if you're really drilling through concrete, get a drill that is not percussive, and then go full speed, and you tell me what happens to the bit. You will get stuck, and it will get so hot that the second time you try to drill, you will not be able to drill even into butter. But if you go slowly, you will not get stuck. You will take a long time, but you will get there. So the ExoMars drill is slow. To get down to 2 meters, it really takes us a few days. Now, regarding what sort of strength of material you can go through, easily through anything that is as, let's say, as hard as a medium marble. So we can do, of course, basalts are super hard, but why? I would say that probably basalts are not your first target of choice. It's probably what we are most likely to find, but we are hoping we will be able to find clays, salts, maybe some sort of other evaporitic deposits, maybe more associated with hydrothermal stuff. Into all those materials, we can drill, and we can drill easily. If we had degraded basalts, like some of the ones that Spirit found on the Columbia Hills, we could probably drill through those as well. But hard basalt, no. And I frankly speaking, I don't see how on earth you could arrange things to drill on basalt with a drill like the one we have today. It's not the fault of the drill, it's the way it is mounted on the rover, the weight, the mass we can bring to bear. It's the 300 kilos of a rover on Mars, it's like 120. It's not a lot of weight. But I don't know if that helped or put you more in despair, but I think for juicy types of minerals we can do a lot. For volcanic rocks, it's tough.
Well, I would expect the types of rocks that could host traces of life to be volcanic sands that would probably have been partially altered to phyllosilicates. So not too tough, but it depends on the cementing material.
I have good news then. because if it is like volcanic sand, which is aggregated more or less loosely, it is true that we cannot drill through basalt, but we can probably collect that. But the good news is that we can crush basalt. So if we are able to get it in, we can even crush hard basalt with a rock crusher.
Yes, but I think more in terms of sediments, altered volcanic materials as sediments, not necessarily pure clays, but sort of halfway between.
Halfway there, yeah.
Halfway there, and also hydrothermal deposits, but not necessarily carbonates. Most likely silica. So those are the. I don't think the sulfates are. I mean, you can't exclude the possibility of them hosting life, but they form so much later on in the history of Mars, at a time when surface conditions were not really conducive to life. I mean, you could have had a miracle, but so okay. Well, that's good news then. If ExoMars could probably penetrate into lithified volcanic sands, just so long as it's not chert as it is in the early Archean stuff.
Oh yeah, chert is even worse than basalt. So
you're telling me, I know. Okay. Well, those were the only questions I had, Jorge. Thanks again, and as Franco said, my best wishes to everybody for this holiday season.